Okay, welcome to Alternative Fuels 3, the third in the lecture videos on alternative fuels. We left off last one on the second one with tidal energy, and now we're moving on to geothermal. So let's look at how it works. Okay, so as you go through the layers of the crust, and we're talking. If we look at this scale, we're talking about some very big layers, 4 to 5 kilometers down. So we're talking 5,000 meters. All right. So you have a really an impermeable, most likely capped area here, and as you go closer to the core of the Earth, you get a increase in temperature. There's a lot of heat in the center of the Earth in the core mostly because of radioactive decay of things like uranium and the like. Lots of heavy elements. And so because of that decay, you can get temperatures 5,000-6,000 degrees, but not quite as hot as that in this area. We're talking 200 or 300 degrees Celsius. So if you can drill down to that area and then create a fracture in the rocks by pumping in high pressure liquids to crack the rocks so that it's very porous, it'll be hot and yet porous. So when you pump water down, that water is heated up by this geothermal heat, and then it returns under pressure to the surface solely by being heated. And as the water heats up, it expands, and it can go through these pipes up to here, where it can be used to either heat water that's cycling through the turbines, or it can go directly through the turbines, and that will create electricity to go out to the grid. Okay. And so it's just a turbine, as we've seen before, and you can, like we said before, you can take either the steam coming directly out of the Earth and turn this generator, or you can use a heat exchanger. Now, the reasons that you might not want to use the heat, this steam coming directly out of the Earth, is because it has a lot of corrosive minerals and other things, lots of oxygen that are dissolved in it that will corrode your turbine quite quickly. So you can use a heat exchanger. You can just directly pipe it through a non-corrosive pipe, and you're going to lose a little bit of efficiency in this heat exchanger, but it's much like a car. All right, so much like the radiator in a car, or a refrigerator, where you have, or an air conditioning unit. But like a refrigerator, you can also, if you use this type of closed loop system in here, where you have the heat exchanger heating up a different liquid, then you can change the liquid. You don't have to use water, because there are lots of liquids that will turn to steam. Most any liquid will turn to steam when it's heated high enough, and they all have different boiling points. So if you use this binary cycle power plant, which is the most recent development, you can accept fluid temperatures as low as 57 degrees from this water coming up here, okay, Celsius. And that is enough to pass through this heat exchanger and heat a secondary fluid with a much lower boiling point than water, and this vaporizes and then drives the turbine. Okay. So, of course, if you're going to use straight water, then in this turbine drive, then you're going to need to heat it up much more than 100 degrees Celsius with the pressures that you need. So, in any case, you use the heat from the Earth to drive the turbine. And just a little bit of information for you here that's quite interesting. A person named Prince Conti tested the first geothermal power generator in 1904 in Italy, and he successfully lit 4 light bulbs. So this has been around for a little while. And it's estimated the amount of heat within 10,000 meters, within 10 kilometers of the Earth's surface, contains 50,000 times more energy than all the oil and natural gas resources in the world. So why don't we just go ahead and build lots and lots of these plants? Well, the positives are that it's very clean. Okay, you're just pumping water up and down. It's renewable because there's a massive amount of heat in the core of the Earth, and will be essentially for as long as we can foresee. And it requires absolutely no fuel transportation. So you can build these things anywhere that you want, but it depends on the closer you are to the ring of fire or the boundaries between plates, the hot spots where, like Yosemite Valley and New Zealand, where we've got a lot of hot pools, and other places around the Pacific Rim. Then you're going to have it's going to be a little cheaper because you don't have to drill down as far, and you could put these very close to your centers of population where you need the energy. The only problem is drilling down to 8,000, 5,000, 8,000 meters is really expensive. And if you want to try to find these hot spots to drill down to them, it's very expensive to drill, to explore. Okay, so because you have to try to find these hot spots, trying to find them, you have to put in hundreds of thousands of dollars worth of drilling, and you may come up with absolutely nothing. And the other thing is they tend to be in seismically active areas, so there's a lot of likelihood that you're going to get earthquakes and the like near your power plants. Okay, which is not going to be too much of an issue with geothermal because there really isn't a lot of pollutants like in a nuclear power plant if you have an earthquake that could cause a meltdown. Okay, so here is our New Zealand geothermal power station and capacity, a little chart. Okay, and you can see the average gigawatt per hour generation, and this is the megawatt capacity, or this is the gigawatt per year annual generation. This is the megawatts that they can produce at peak loads. And the year they were commissioned, so 1958 was the first one. And so we produce 7,223 gigawatts through geothermal power generation out of the 42,900 gigawatts we use per year. So we've got a long way to go, but this will definitely be an increasing part of our power supply. Okay. We'll move on to solar thermal. We're still on thermally heating water. Okay, and but we can use the sun's energy to do it. So these are two interesting arrays. This one has a tower in the center, heating and cooling, and this tower has a receiver. Okay, and what that is a big vessel that heats up because every one of these mirrors is pointed, so is arrayed so that its reflection, the sunlight that it reflects, goes directly onto this central point. And with all of these reflecting light into this central point, that is enough to heat this to huge temperatures. and you can cycle water up into this boiler, and that will vaporize the water. It'll boil it and send it down as steam to your generator, okay, to your turbine, and that will generate power. And then we have another type of generator that will also superheat water to steam to drive a generator. The turbine would be located here in these central buildings, and what we have here are these troughs. They're parabolic arcs so that they will, no matter which way the sun comes in, it will reflect onto a central pipe here. And this pipe is heats the water that is piped into it, and as the water flows through these pipes, it heats up and heats up and heats up until eventually it becomes so hot that it's steam, and it will go to a central collection pipes and drive a turbine. So there's enough pressure here from the water vaporizing into steam that it all comes to a central collection point and vaporizes, and drives a turbine, and that will create power. So obviously, what are the problems with this? Well, all night you're not going to be generating any power at night, and if it's cloudy, you're not going to be generating any power. And the temperature, the atmospheric temperature, of course, will make a difference with these pipes as well. So you can put these things into the desert, where you're hopefully going to have lots and lots of sun all the time. It's going to be quite hot, and that is your best emplacement. But you're not going to necessarily be always able to generate power out of these things. And you can see that they're fairly expensive to build. But once they're built, then they're passive in terms of collecting heat, and so you have probably you have no fuel to transport, and potentially they will last for quite a long time. Okay, so that is heating water through the sun's energy, and we'll move on to wind power. All right, we've got our old friend, the turbine, which is a generator. Okay, as long as you've got something turning a shaft, and you've got copper wires coiled around it, that is going to generate electricity. And so you have your blades with the wind. You've all seen hopefully you've seen these. If you drive over to Raglan, you'll have passed a wind farm. And I'm sure you've seen lots of pictures of these things. And so the nacelle is this area here. The generator is housed in the nacelle, and then you have a big tower with a power line that runs down, and then a power line that connects out to the national grid. All right. So, how's this? Is this going to be a replacement for fossil fuels? Unfortunately, it won't be a complete replacement for fossil fuels. It's good in certain areas. It's very useful in certain areas. It's going to be more and more. There's going to be more and more capacity through wind power over the next few years. The positives, it's well understood. It's been used for thousands of years. You can imagine thinking about the windmills on in the Dutch countryside and other places. It's been used usually to pump water, and it's clean. It's renewable. It's relatively cheap compared to certain other renewable power sources. It's not as cheap as oil at this point, but that's not very far off. That it'll probably be cheaper. The only thing is that it's not always windy, and people don't like them. There's a lot of NIMBY with this, not in my backyard. So it's very hard to get the resource consents to put these things up on top of ridge lines and hills, and usually in places that are sort of iconic for their view, which is why a lot of people move there, and so they don't want to necessarily see one of these turbines up on their, or usually a huge array of these turbines up on the ridgeline of their view. Also, they do kill birds. Not everywhere, but there are certainly places that were commissioned and then decommissioned in California, where California condors were flying into these, and a few other raptors like hawks and the like. Now, the early generation ones spun at much higher rates. These ones spin quite slowly, so they're less likely, supposedly, to kill birds. And we don't seem to have much of an issue with this in New Zealand. But other places they may have an impact on, especially if they're put into the migration routes of certain bird species. And they also make a bit of noise. If you go down to one of the marinas and have a listen on a windy day, you'll hear a few turbines on sailboats, and you'll be able to understand how these things that make noise as they're traveling through the air. And if you go to the ones in Raglan, you can hear them going whoop, 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 like that. So perhaps you might not like to have that near your house if you live near one of these things. Okay. All right, so we'll move on to another one, heating water. Well, we produce a lot of stuff that we throw out. Okay, and a lot of that stuff is flammable. And everywhere that we have human populations, we produce lots of stuff and throw it out. And in a lot of places, there are a lot of places where people have chosen to build power plants where you heat up water by burning this stuff, and then as the water heats up, it boils and goes through a turbine to generate electricity. And there are some positives about it. So first off, we've got a lot of rubbish that we need to get rid of. So it is fairly renewable. And we're probably always going to have rubbish as long as we're living in the way we do. It's just a giant stack of newspapers and cardboard. Alright, this is available everywhere that humans are. It's very low carbon emission, because essentially all of this stuff, in order to produce it, well, this might be a little bit different with plastics, but in order to produce all of this stuff, we've cut down trees. So those trees this is carbon that has already been taken out of the atmosphere, so it's really carbon neutral to burn newspapers and the like. And so the waste, it's good to be able to get rid of waste so we're not filling up landfills. Now, there are some problems with it. Okay, it's very energy intensive. If you look at this, okay, this is where this is a pile of stuff that can be used to burn. Okay, all of this extras from wood chipping and from logging. This big machine, it's doing something with processing logs. I'm not sure exactly what, but you have a refuse pile. But you have to truck that refuse. The logs are not always in the same place. They're not always processed in the same place. So all this refuse that's not going to be suitable for paper production could go and get burnt, but it has to be trucked there. So you've got to use a lot of oil and resources in order to get your waste to the plant. Not totally clean to burn, especially if you look at a pile like this. There's going to be a lot of little bits of rubbish. There's if you look at any newspaper, the glossy print in a newspaper, all of that is sealed with a plastic. It is a petroleum-derived plastic coating on glossy newspaper. And plastic bags and cardboard is full of glue that holds the layers together, the laminates together. And so when you burn it, might be producing dioxins or who knows what else. And so you need to have very expensive scrubbers to get rid of that type of pollutant. And it could be seasonal. So this picture is actually from Norway. And in Norway, in the winter, they don't do a lot of logging. It's too cold. In the summer, they do a lot of logging, and they have a lot of this material to transport. And they are using this stuff to power a electricity generating plant. But this is only available part of the year. Okay. So, rubbish incinerators are a source of electricity, but will only be limited in their use. Okay. How about nuclear power? All right. Positives. There's very little carbon dioxide emission, and it is continuous and predictable. So you can, by inserting more or less fuel rods, control exactly how much heat is coming out of the nuclear decay that is happening with these controlled reactions. And in class, I'll diagram out how nuclear power creates heat. And there are 62 power plants, nuclear power plants, under construction worldwide. So the only CO2 emission really is in building the plants. Once you build the plant, you can have you can generate lots and lots of power. There's very easily. Okay, and very predictably. Okay, but what's the problem? Okay, the waste is really, really nasty. All right, so you've got spent fuel that is still radioactive and will be for tens of thousands of years. So whatever we create in terms of enriched, very radioactive fuel, especially spent fuel, then it is going to be stored with thousands of generations stored, and be an issue for thousands of generations of humans to come. So we really don't know what we're passing on to people in the future. Okay, there's a lot of environmental damage with strip mining for uranium, and also the catastrophic consequences that we've seen over the last few years are really devastating. And if we think about what the risks are, then there's a good question of whether there's a very reasonable question to ask: is it worth it to create these power plants? Now, you've got Chernobyl, and you've got, of course, Fukushima, and nearly a meltdown at 3 Mile Island in the States. And so we've got 3 in the history of nuclear power plants in a 50 to 55-year history of nuclear power plants. We've got 3 two hugely catastrophic disasters and 1 near catastrophic disaster. And so if you extrapolate that rate of disasters to the future, then it's certainly worth asking whether it's worth the risk. So this area, this exclusion zone, is where the wind has carried radioactive particles from this Chernobyl nuclear power plant. Many, many people died in trying to cap this thing with concrete and get it so that it was safe. The concrete is now, after only about 20 years, 25 years, something like that, the concrete is deteriorating thanks to the nuclear decay and the heat produced in it, and so that will have to be recapped at some point. But all of this area you can go into for a few hours at a time only, unless you're wearing protective gear. This area, it used to be a huge food-producing area of southern Europe, and now is a no-go zone. So we've got water flowing through it, through this river through it, which may pick up radioactive particles. Still being used, and this area is now completely off limits. Interestingly, though, it's turning into a bit of a marine park. There's a lot of wildlife living in there, like bears and wolves and deer and everything that seem to be thriving. So, anyway, if you were to go and live in it, there are people who are actually living in this zone, and they just decide that they're going to accept a short life with cancer as their end, and just happily live in that area. So we'll see what happens with Fukushima as well. Okay, wave power. So a terawatt is equal to 1 trillion watts, and we use about 16 terawatts in 2000. This was 2006 worldwide. We're up to almost 17 now. But this could produce about 2 terawatts if we were to use wave power in near most of the major centers of population around the world. And so it's completely renewable. It's always going to be there. As long as there's wind blowing, then you're going to have waves. And so if you have waves, then you can build machines that can transform that energy from the wave into motion, into a cyclical motion to drive a turbine. And it's very clean, as long as these things are removed from the environment once they're taken out, or once they've come to the end of their life. They can be sited offshore, so they don't take up any land. Very reliable, and we've got lots and lots of different designs for wave machines. We'll have a look at some of these in class. But you can see with this one, it's quite interesting. It flexes here, so as this thing goes up, and this end comes down, as the wave passes, then that flex generates mechanical energy, and it turns a turbine shaft and generates power. Okay. So the interesting thing about these things, or one of the interesting things about these things, is that they're supposed to be quite reliable. But it's, as we all know, it's very, very difficult to build things that work in the ocean. It's very, obviously, very corrosive environment. And there was a wave buoy, a trial wave buoy that was just put in off of Oregon, and it was supposed to have a 100-year duration. It was built to supposedly last for 100 years, and it sank within a year and a half. But so these things are very expensive to try to design so that they will be robust enough to handle no swell one day and 7 or 8 meters the next day. And you can imagine, anybody who's a surfer or been swimming in reasonable sized waves knows how much power there is in these things. So this one is one that would go up and down with wave action. We also don't know what sort of effects these things might have on sea life. All right, maybe they'll be great artificial reefs. Maybe they'll cause a lot of noise pollution, though, and drive marine mammals away. You tend to have lots of, if anything that is in the ocean and is a hard surface, will also be a good growing surface for all of the invertebrates that we've studied. And so these things are going to get fouled very quickly, and that can cause problems. So that's very expensive to keep these things clean. And if you put anti-foul paint on, then it has to be continuously reapplied, and also has its own environmental concerns. And they may be a navigational hazard. So if you have something like this and a ship drives into them, like Arena, then that is going to muck up your ship and your power generation. And they may be visual pollution as well. So sometimes, again, people might not want to look at these arrays of these things off of the coast. Okay, but there is a lot of potential, and if we can safely, cleanly use wave power, then it is completely renewable and produces no carbon dioxide or waste. All right, we'll move on to photovoltaic. All right, so this one, rather than moving a turbine, actually you converts solar irradiance directly into electricity. Okay, so these photovoltaic panels pick up the sun's rays and then convert that into electricity, which is stored into a battery and then discharged from the battery directly into a power line, okay, through an inverter, or directly into a power line for a direct current for driving things like 12-volt power systems on boats and the like. You'll see these quite often. Okay, everything in your house that you convert into will be, or that you plug something into, will be an alternating current. Okay, so photovoltaic. So the positives: it's very renewable. There's always going to be sunlight, as far as we can see, and as long as the planet's around, there's going to be sunlight. And eventually, there's going to be so much sunlight that it'll destroy the planet. But it is renewable. It's abundant. The prices are coming down on the panels as they get more and more mass-produced, and they can be located anywhere and scalable. Okay, so just another word on the prices. Right now, it's more expensive than using fossil fuels to generate power. But as fossil fuel prices go up, these things will become more competitive in terms of generating power. And these can be located anywhere and scalable. So you can have a giant system like this, or you can have a few panels on your boat or on top of your house. Right now, the payoff in terms of the power that you save, it takes about 25 years to pay off what an installation on the roof of your house would be. So that's quite a big outlay for most households to plunk down $20,000 or $30,000 on a photovoltaic system. But they are very cheap. Very clean, and produce no pollution, no CO2. The problems the sun. It's not always sunny. Okay, and the batteries do require a lot of pollution in their manufacturing process. They tend to create a lot of lead contamination, and like when you're building batteries. They take a lot of space, and if you think about this array, that's probably all arable land that could be used for crops. You could see that there's other stuff growing. It's flat. It's sunny, which is all good for growing crops. And so these things do take a lot of space. Now, that can be mitigated by putting these things on top of roofs and the like. But the panels do wear out, and that you may have a 10 or 15 year, possibly only duration of the lifespan of a panel. So you may have to replace them after 10 or 15 years. Okay, moving on from photovoltaic. energy, we move on to hydrogen fuel cells. And you can have a look at this URL right here, and we'll look at it in class, but this is a little bit of an explanation of how hydrogen fuel cells work. Essentially, you take water, and using electricity, you split it into oxygen and hydrogen. And then you store the hydrogen, release the oxygen, or use the oxygen for medical use or whatever else that you need to use it for. And then you store that hydrogen, transport it to wherever you have a hydrogen burning engine, and then you burn it, and it recombines with oxygen, produces heat, and that burning, when you produce that heat, can be used to create electricity. And the only byproduct of that is water vapor. So it's completely clean when you burn hydrogen. There are no moving parts or noise in electric cars. This is scalable, so you can have very big or very small hydrogen electrical generation. And you can store the excess electricity in the form of hydrogen. So this is if you generate more electricity than you need, you can use it to create hydrogen and store it. So that is then usable at a later time. So let's say you build a photovoltaic system, and when the sun is shining, you actually produce way more electricity than you need in that area. Well, you can use the excess electricity to create hydrogen and store it and burn it when you are, well, when the sun's out, or not out, when it's dark. Okay? So it's a very good system, but the problem is that the catalysts that are used in order to break the water down, okay, you have to have this this catalytic surface in order to break water when you pass electricity over it into the oxygen and hydrogen. And it's not yet readily available, so we don't have hydrogen stations where we can go and fill up our cars with hydrogen. So the infrastructure in order to have hydrogen pumps like we have petrol pumps all over the place would cost massive amounts. The safety, okay, hydrogen was used in the Hindenburg, and we've probably seen videos of this, but as soon as a tiny little spark happens around hydrogen, it explodes. It's very, very flammable. And so if you have tanks with this stuff in every car going down the road, you're going to have some issues. And the other problem is, of course, in order to generate the hydrogen in the first place, you have to pass electricity over these catalysts, and you have to have some sort of energy source that could be used in another way in order to make the hydrogen. So really it's just transporting the energy cost downstream to some other method of generation. Alright, let's move to biodiesel, ethanol. Okay, so biodiesel, we can produce lots of biodiesel. We'll talk about this in class as well, but every plant will have some amount of fat, and just like most living organisms will have some amount of most living organisms will have some amount of protein, some amount of carbohydrate, and some amount of fats making up their tissue. All right, some plants will have a lot of oil, which is the fatty portion. Okay, and you can get saturated fats or unsaturated fats, and some of those fats are in liquid form. Those are oils. Okay, so if you squeeze olives, then you can get olive oil. Okay, and what other oil do we get? Palm oil and the like. All right, so when you grow these plants and then use the oil and burn it and create biodiesel, or you ferment the carbohydrates in the plant and you get alcohol that you burn, and that is the ethanol. You can mix that with gas, or you can burn it straight. And you can power things like Arnold Schwarzenegger's Humvee with biodiesel, and that's completely carbon neutral. It produces carbon when it burns, and it is the carbon dioxide that is produced, though, is carbon that has been taken out of the atmosphere. And essentially with the waste products, the extra products of the cellulose and the like that is produced by the plant, you're probably going to have a net decrease in carbon by producing biodiesel. So with a lot of vehicles, you would, and depending on what rate you mix the diesel with the lipids from plants, the oils from plants, you can put it straight into cars that are already running on diesel. So you don't have to do any conversion. You can do it with a slight conversion with your injectors so that they don't gum up. You can pour chippy oil straight into your tank, and then with filtering out the little bits of chips, of course, and burn that and drive down the road. And I've heard that those vehicles actually smell a bit like a fish and chip shop. So this is great, as long as we don't turn all of our land that we grow for crops into biodiesel producers. So most of the biodiesel right now comes from corn, and corn we could just go ahead and eat. So there are major problems in terms of population growth with producing biodiesel. And when you put this corn towards producing biodiesel, then the price of corn for human consumption goes up. And right now it's more expensive to produce biodiesel than it is to pump and ethanol than it is to pump this stuff out of the ground. Okay, but the caveat of that is that biodiesel can also be produced from algae. Alright, now we think about algae for a little while. What does algae need to grow? Okay, algae needs water, and it needs nutrients in the form of nitrogen, phosphorus, and a few other micronutrients, and what else do we need? Nitrogen, phosphorus, silica, lots of other little micronutrients. But what do we have in terms of our major problem in keeping waterways clean? Well, of course, it's the input of nutrients into those waterways. So we have the problem of fouling our waterways with excess nitrogen and phosphorus. This comes from animal waste and from human waste. And so when we get eutrophication of water systems, perhaps we could mitigate that by growing algae. Okay, so algae is really something that's magic and could be a major part of our oil production in the future. We can grow oil in the ground. Essentially came from millions and millions of years of plants growing, and then the lipids from those plants being decayed and seeping down and being deposited in petroleum products. We can take the middleman out of the millions of years of decay and grow specific strains of algae that can produce up to 50% of their weight as lipids, which is pure oil. Alright, so that means that if we the other thing that algae needs to grow is carbon dioxide. So if we think about what we're doing with the atmosphere, we are increasing the carbon dioxide content of the atmosphere greatly, which is something that we don't want to do. So if we can put algae growing in and reduce some of the externalities that are, or actually put some of the externalities into the price of producing carbon dioxide, this may become a much more economically viable way to grow oil and mitigate some of our environmental problems. So you put these things into an area with lots of sun, and you grow algae in these big bags or other grow-out systems. You stream wastewater through these bags. A lot of the nutrients are taken out of that wastewater, so you get cleaner water coming out of this by growing plants in it, and you reduce carbon dioxide. And the byproduct of this is oxygen and the algae. So in the future, algae could be a very, very big part of our alternative fuels. And one of the great things about this is you can produce, if we're going to grow biodiesel, you can produce 30 times more biomass for the same amount of area by growing algae than you can by growing terrestrial plants. And that is the end of our lecture on alternative fuels. See you in class.